Yeah, it's filming.
Yeah, but my trackies are completely windproof.
Here we can see two servo motors spinning in phase.
Oh, you want me to
Great.
go like
Let me subtitle that later.
Hi kids! Today I'll be talking about central pattern generators, or CPGs. So, what is a CPG? CPG. Central pattern generators are biological neural networks that can produce rhythmic pattern outputs. Great about this is this works without sensory feedback, so it wouldn't have to be connected to our brain, for example. Which is why it's used, for example, in digestion, I guess, how the intestines move, can produce food, and this would arguably work, or heartbeat also, for example, I suppose, without the brain. So how this was tested, for example, is they extracted the spinal cord out of a lamprey, which is the fish that we also had in class, and it would still produce the same rhythmic pattern, locomotion pattern that it did when it still was connected. So yeah, basically in robotics this is also really useful. We can use a fairly simple model to create movement patterns. Alright, so what we will be using are phase-coupled oscillators. At least two we need to actually do this. So we'll be driving servo motors, so I will always stand for the ith servo motor that we're driving. Theta here is the output to our servo motor, and of course we're making oscillations, so we will be needing R, which is the amplitude, we'll be needing phi, which is the phase, and x, which is the offset. So I think you all know how an oscillation actually works, so I don't have to go too deep into this. Now, we can't directly calculate the R, the phase, and the amplitude, phase, and offset, but we can calculate their derivatives. So I will be explaining these here, and I'll be starting with the most difficult one, the phase derivative. So this is the change in phase that we'll be experiencing from one time step to the next, and we'll be later we will have to numerically integrate this to actually get to our phase value. Now, the base of the change in the phase would be 2 times pi times the frequency at which we're running. So this is the base speed at which our servo motor would be spinning. What we see here, the summation term, is first of all we want to sum over j not equal to I, because we won't look at elements and their phase correlation with themselves. So this summation term starts with our weight from I to j, which is a certain, let's call it the phase coupling term. This could be 0 or 1, could be something else, to introduce different relationships between elements. R, of course, is the amplitude. We learned in class that actually scaling this term, I'm going to get to it in a second, by the amplitude makes it a bit more stable. Now inside the sign, we basically are looking at an error term. This is the phase of j, this is the phase of I, and this is what we're going to call the phase offset. So phase of j minus phase of I is basically just an error. If we look at two things spinning in phase, if you would subtract these from each other, we would just be ending up with an error of 0. But maybe we want them to spin out of phase, so we could introduce a phase offset of, I think it's pi, yeah, that would flip it by 180 degrees, to make this go like this, right? That way we can introduce the phase offset like this, or something like this. Exactly. We put this inside the sign to scale it between 0 and 1. And we multiply it by the amplitude and the weight term. And this is what we're going to add on top of our frequency to actually introduce these phase relationships between elements. Exactly. Then we have to look at R, at the amplitude. So the derivative of the amplitude we can see is defined by an A term. So this is just some constant that we by which we define it, so sort of like the proportional term of a PID controller. How fast do we want this to change? Where R of I is the reference amplitude, and Ri, so the capital R of I is the reference or the target amplitude, and Ri is the actual amplitude. So we look at the error, again, error term, and we'll multiply it by a constant to proportionally scale this. Same we have to do to not get really jumpy offset changes, have to do for the offset. So we'll be looking at a b, another constant term, and we have here our chi I, which is the target offset, minus the offset that we have at the moment, multiplied by our constant, and voila, we end up with the derivative term. So how do we get from the derivative to the actual values? Easy. We're going to use Euler integration. It's of course the simplest numerical integration formula. But yeah, in the example of phase, phi, we can look at phi at time t is equal to the phi at time t minus 1, the times that we had before, plus the derivative of t minus 1, so we're going to use this formula here of phi, times the actual time step delta t. And that way we can get to our phi of t. Similarly also r and x, and t of course would be y in this case. Yeah, and then we can fill in all these values to actually drive our servo motors. Now let's have a look at the code. Now here we have defined our struct as a type def struct, so this makes it easy for us to define an oscillator. It's called oscillator. What we added to the code that we were given is the offset target, because yeah, we want smooth transitions in case we change our offset. Because later in the code you'll see we're actually using, we're inputting these at runtime to see how changes affect the behavior or the locomotion of a robot. Now, let's look at the CPG method. It's basically just the implementation of these formulas, which is really simple, but about one slight issue that we have with the implementation I'm going to go into. This is the phase, because we're looping over the phase here multiple times, and we're changing the phase inside this loop. So what we don't want is we don't want to change the phase, and then in the next iteration of the loop, where we're assuming to be working on, this is this part here, we assume to be working on the ith phase term and the jth phase term, but actually the ith phase term might have changed inside this loop. So because of this, we will we first loop over the elements, and we save the phase terms in a separate variable phase, so this array phase here. So this is the one we will use inside this for loop that actually calculates, recalculates the amplitude and offset terms, as well as the phase dsum, which is basically this term here, this summation term here. Once we did that, at the end we can update the phase term inside our oscillator using, we use the phase array inside here, and then later we can update the actual phase term and the position. One more important thing is we had to scale the dt by 0.001, because it turned out, okay, if we use integers for this, we ended up getting, because of this, 2 times pi that we're going to feed into the sine, we ended up getting zeros and nothing changed. Then we have a couple of helper methods here. I'm just going to quickly talk about it, because I said, yeah, we can actually modify all these control values. So these are the target amplitude, the target offset, as well as the phase offsets. We can define this on runtime. So for this we need certain serial methods. First of all, we can print out the parameters. This is not interesting. Here we have a little serial buffer method that reads from the command line. So we can actually type something in, and the parse cmd method will parse this into whatever we want. So in our case, yeah, we just define, for example, if we put dt and then a value, this will change the dt. If we say, for example, a and a value, then this means, okay, no, actually a0 and the value, this will change the amplitude, the target amplitude for the 0th element to this value.
Alright, here we see 2 servo motors running out of phase with an amplitude of 60. Now we will change the amplitude of the first one to 20 and the amplitude of the second one to 100.
We're already missing the first one. We're doing first in phase.
Ah, okay. Here we can see 2 servo motors running out of phase with an amplitude of 60. First we will try to make them run in phase. Now they're running in phase, and we will change the amplitude of the first one to 20 while increasing the amplitude of the second one to 100. Beautiful.
Sure.
Now we will give them both the same amplitude again, an amplitude of 50, and then we will make them run with a different offset. So the offset of the first one will be minus 50, and the offset of the second one will be plus 50.
There we go.
All right. Now we will change the frequency. We'll increase it to a frequency of 2.
Let's just back to 1.
Bit less. All right. Now we will introduce a phase lag. We will choose -1 for the first one, the phase bias, and 1 for the bias of the second one.
There we go.
All right. That's it. Okay.
Where should you upload? Important detail. Phase bias of 2. Oh. Oh. The amplitude of the middle part is now 80. 85 actually. Oh Jesus! It hits the Arduino. Amplitude of 60 in the middle part. The rest is just 0. So it does not move forward. Okay, this one is the amplitude of 60 and this one as well. They have a phase bias of pi. Okay, I'll have an amplitude of 60. Oh! And there's a phase bias of pi here, and a phase bias of 2 right here. Okay, and now there's an offset of 25 in the middle.
That's not wrong. What does that mean?
And now there's a frequency which is almost 2 times as fast, as you can see.
The pusher.
What a rep! Oh,
It doesn't work.
pusher version 0. See, now it's great. Yeah, presumably so. Oh.
Okay, film.
2, 1.
Yeah, that's it. There you go, red one.
Yes. Yes.
Look at that noob.
It's the one and only Digo Double G. You know I'm mobbing with the D.R.E.
Yeah. You know the West Coast is back for